In this tutorial, we will be discussing energy and chemical and physical change in temperature. Systems with high potential energy have a tendency to change in a way that lowers their potential energy. Objects or systems with high potential energy tend to be unstable. Some chemical substances, such as molecules that compose TNT, trinitrotoluene, have a relatively high potential energy. Energy is concentrated within them. TNT molecules tend to undergo rapid chemical changes that lower their potential energy, which is why TNT is explosive. In chemical reactions, there are two different terms to describe the energy within the reactions. One is exothermic, which means energy is released. The other is endothermic, which means energy is absorbed. We will be discussing this further in later tutorials. The atoms and molecules that compose matter are in constant random motion. They contain thermal energy. The temperature of a substance is the measure of the quantity of thermal energy. The hotter an object, the greater the random motion of the atoms and molecules that compose it, and the higher the temperature. We must be careful not to confuse temperature with heat. Heat, which has units of energy, is the transfer or exchange of thermal energy caused by a temperature difference. For example, when a piece of cold ice is dropped into a cup of warm water, thermal heat or thermal energy is transferred from the water to the ice. Temperature, by contrast, is a measure of the thermal energy of matter, not the exchange of thermal energy. Which brings us to ways of measuring this. There are three different temperature scales that are common in use: Fahrenheit, Celsius, and Kelvin. On the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and boils at 212. On the Celsius scale, water freezes at 0 degrees Celsius and boils at 100. And then finally, Kelvin, which is what's used by scientists, avoids negative temperatures altogether by assigning 0 Kelvin to the coldest temperature possible, absolute zero. Absolute zero is the temperature at which molecular motion virtually stops. So let's take a closer look at these three temperature scales. Here's Kelvin, Celsius, and Fahrenheit. If we look closer at Celsius and Kelvin, their temperature gradients are the same. There's a 100 degrees difference between 273, where water freezes, and 373, where water boils, and 0 degrees Celsius and 100 degrees Celsius. However, there is a difference with Fahrenheit. The Fahrenheit degree is 9/5 the size of the Celsius degree. In other words, there's 180 degree differences between when water freezes and when water boils. So you're going to notice a temperature change faster with Fahrenheit. We can convert between the Fahrenheit, Celsius, and temperature scales by using the following formulas. K for Kelvin is equal to degrees Celsius plus 273.15. And degrees Celsius is degrees Fahrenheit minus 32 over 1.8. This 1.8 comes from 9 divided by 5, which is what we said right here, 5/9. So let's do some practice problems with these. Convert 42 degrees Celsius to Fahrenheit and express the answer in the correct significant figures. So we're going to be using this equation on the bottom because it has Celsius and Fahrenheit. So 42 is equal to degrees Fahrenheit minus 32 over 1.8. First thing I want to do is multiply by 1.8 to get everything on top. So therefore 42 times 1.8 is 75.6. Now to get degrees Fahrenheit by itself, I'm going to add 32 to both sides. And that comes out to be 107.6 degrees Fahrenheit. The 1.8 and the 32 are part of the definition within the equation. So I'm going to focus on 42 for my significant figures. I have two sig figs there. Therefore, I need to have 2 in the answer. That brings me to 110 degrees Fahrenheit. Let's try the next one. Degrees Celsius to Kelvin. If we look back at our equations, Kelvin and degrees Celsius are in the top equation. So Kelvin is equal to degrees Celsius plus 273.15. So that means Kelvin is equal to 97 plus 273.15. Which then brings me to an answer of 370. Notice with the significant figures, we're adding here. So that means I want to look at the place values rather than the quantity of significant figures. This is in the ones place. This is in the hundreds place. Therefore, I want my 0 at the very end to count. So that means in order to do that, I have to put a decimal after that, because trailing zeros with decimals are significant. We're going to try one more, and this time we're going to put the two equations together. Notice here we're going from 233 kelvins to Fahrenheit. There's no way to get from kelvins to Fahrenheit without using both equations. So that's what we're going to do here. So 233 Kelvin is equal to degrees Celsius plus 273.15. First thing I'm going to do is subtract it across. That gives me a degree Celsius of negative 40.15. Now I'm going to take this number and put it into the other equation. Negative 40.15 is equal to degrees Fahrenheit minus 32 over 1.8. Multiply both sides by 1.8. That gives me negative 72.27. And then add 32 to both sides. And that gives me, once again, negative 40.27 degrees Fahrenheit. And that's how you use the temperature equations.